Welcome to this lecture on the fundamentals of biomolecules. Today, we are diving into a fascinating topic called isozymes. Have you ever wondered how your brain and your liver can process the exact same nutrient, but in completely different ways? Or how doctors can use a simple blood test to know exactly which organ in your body is damaged? The answer lies in isozymes. These are remarkable molecular machines that allow our bodies to fine-tune chemical reactions to meet the unique demands of different tissues. Let us begin our journey to understand how they work. To start, let us imagine you need to deliver packages across a large country. In a crowded, narrow city, you might use a small, nimble bicycle courier. But for long, open highway stretches, you would use a massive delivery truck. Both the bicycle and the truck are performing the exact same fundamental task, which is moving a package from point A to point B. However, they are built differently because they are optimized for completely different environments. In the human body, enzymes face a very similar challenge. An enzyme working in the oxygen-rich heart needs different features than one in an oxygen-deprived skeletal muscle. This is why nature created isozymes. Now that we understand the analogy, let us look at the formal biochemical definition. Isozymes, also known as isoenzymes, are multiple, distinct forms of an enzyme that catalyze the exact same chemical reaction. Despite performing the same catalytic function, these enzymes differ in their amino acid sequences. This means they are encoded by different genes or arise from different combinations of polypeptide subunits. Because their physical structures are slightly different, isozymes typically possess different kinetic properties. For instance, they might have varying affinities for their substrates or different maximum reaction velocities. They also differ in their regulatory mechanisms, meaning they respond differently to inhibitors or activators present in their specific cellular environments. Building on their biochemical properties, why are isozymes so essential for us? The existence of isozymes is absolutely crucial for the survival and efficiency of complex multicellular organisms. Without them, every tissue in our body would be forced to metabolize substrates at the exact same rate, regardless of whether the tissue is resting or working vigorously. For example, the liver needs to store glucose only when it is abundant, while the brain needs a constant, steady supply of glucose at all times. Isozymes allow these organs to handle the same molecule in completely different ways. Furthermore, in modern medicine, isozymes are incredibly important diagnostic tools. Because specific isozymes are localized to specific organs, detecting high levels of a particular isozyme in the blood can pinpoint exactly which organ has been damaged. To truly understand how two isozymes differ, we must look at their kinetic properties mathematically. This brings us to the fundamental equation of enzyme kinetics, the Michaelis-Menten equation. The formula states that V equals Vmax times S divided by Km plus S. Let us break down these symbols. The variable V represents the initial velocity or rate of the reaction. Vmax stands for the maximum velocity, which occurs when the enzyme is completely saturated with the substrate. The variable S in brackets represents the concentration of the substrate available in the environment. Finally, Km is the Michaelis constant. This is a crucial indicator of the enzyme's affinity for its substrate. A lower Km means a higher affinity. If Km increases, the affinity decreases. Now that we have our mathematical tools, let us look at a classic real-world example involving the phosphorylation of glucose, which is the first step of glycolysis. This exact same reaction is catalyzed by hexokinase 1 in the brain and by hexokinase 4, also known as glucokinase, in the liver. The brain isozyme has a very low Michaelis constant of 0.05 millimolar, meaning it has a very high affinity for glucose. The liver isozyme has a much higher Michaelis constant of 5.0 millimolar. We want to calculate the reaction velocity for both isozymes when the blood glucose concentration is at a fasting level of 5.0 millimolar. For the sake of comparison, we will assume both enzymes have a normalized maximum velocity of 100 units. Let us apply the Michaelis-Menten equation to see how the brain isozyme performs under these fasting conditions. We are given a maximum velocity of 100, a substrate concentration of 5.0, and a Km of 0.05. We substitute these values into our formula. The numerator becomes 100 times 5.0, which is 500. The denominator becomes 0.05 plus 5.0, giving us 5.05. Notice that the denominator is very close to the substrate concentration itself, indicating the substrate vastly outnumbers the Km value. Dividing 500 by 5.05 gives us a final velocity of approximately 99.01 units. This physically means that even at fasting blood glucose levels, the brain's isozyme is operating at 99% capacity, ensuring the brain gets a constant, uninterrupted supply of energy. Now, let us perform the exact same calculation for glucokinase in the liver. We use the same maximum velocity of 100 and the same fasting substrate concentration of 5.0. However, this time we substitute the liver isozyme's specific Km value, which is 5.0. The numerator is again 500, but the denominator is now 5.0 plus 5.0, which equals 10.0. Notice that the substrate concentration is exactly equal to the Km value in this scenario, which is a critical kinetic threshold. Dividing 500 by 10 gives us exactly 50 units. This physically means that during fasting, the liver isozyme is only working at half capacity. It leaves the majority of the blood glucose for the brain to use, perfectly illustrating metabolic regulation. To visualize the calculations we just performed, let us look at this kinetics comparison graph. On the horizontal axis, we have the substrate concentration, which is the amount of glucose. On the vertical axis, we have the reaction velocity. The dashed line at the top represents the maximum velocity. Look at the steep curve for the brain's hexokinase. It shoots up and reaches maximum capacity almost immediately, even at very low glucose levels. Now, look at the gradual curve for the liver's glucokinase. It rises much more slowly. The dashed lines dropping down to the horizontal axis show the Km values, which is the concentration needed to reach half of the maximum velocity. This diagram beautifully captures how the brain is greedy for glucose, while the liver is patient. Moving forward, let us examine another vital example of isozymes in action, lactate dehydrogenase, or LDH. This enzyme converts pyruvate to lactate. LDH is a tetramer made of heart and muscle subunits. The heart isozyme, LDH1, has a unique property. It is strongly inhibited by high concentrations of its own substrate, pyruvate. In contrast, the skeletal muscle isozyme, LDH5, is not inhibited by pyruvate at all. We will analyze a scenario with a high pyruvate concentration of 10 millimolar and a Km of 1 millimolar. Both isozymes initially start with a maximum velocity of 200 units. We will see how this substrate inhibition completely changes the way the heart and muscles respond to intense physical stress. Let us calculate the operating velocity for the heart isozyme under these high pyruvate conditions. First, we must account for the substrate inhibition. We are told the effective maximum velocity drops to 20% of its original value. So we multiply the initial 200 units by 0.20, giving us a new effective Vmax of 40 units. Now we plug this effective Vmax, the substrate concentration of 10, and the Km of 1 into our equation. The numerator is 40 times 10, which is 400. The denominator is 1 plus 10, which is 11. Dividing 400 by 11 gives us approximately 36.36 units. This strong inhibition forces the heart to stop converting pyruvate to lactate, encouraging the heart muscle to use the pyruvate for aerobic respiration instead. Finally, let us calculate the velocity for the muscle isozyme, LDH5. Because the muscle isozyme does not experience substrate inhibition, its maximum velocity remains at the full 200 units. We substitute Vmax as 200, substrate concentration as 10, and Km as 1 into the equation. The numerator becomes 200 times 10, which is 2,000. The denominator is again 11. Dividing 2,000 by 11 gives us approximately 181.81 units. This is nearly its full maximum velocity. Physically, this means that during intense exercise, when pyruvate builds up, the skeletal muscle can rapidly convert it to lactate to keep generating energy anaerobically. The stark contrast between the heart and muscle perfectly demonstrates how isozymes protect the heart from lactic acid buildup while allowing muscles to push through stress. We have covered a lot of ground today, so let us summarize the key takeaways. First, we learned that isozymes are remarkable evolutionary adaptations, multiple versions of the same enzyme that catalyze the exact same chemical reaction. Second, by altering the amino acid sequence slightly, nature gives these isozymes distinct kinetic parameters, like different Km and Vmax values. Third, we saw through our calculations how these differences ensure that organs like the brain, liver, heart, and skeletal muscles can manage their metabolic needs independently and efficiently. Understanding isozymes is fundamental to biochemistry, and it provides critical diagnostic markers that save lives every day. You now have a solid understanding of how isozymes function. Great job!